Alright, for number 2, we need to find a Maclaurin series for the following function here. We have f of x equals x cubed cosine of 2x. So obviously in this case, we have a compound thing. We're going to have to do a couple of different steps. We always want to start with the function which you already know the expansion of. And remember that multiplying by x cubed or having the 2x here is relatively simple stuff. We need to start with just what is the Maclaurin series for cosine, and then we'll modify everything off of that. So remember that cosine of x is the sum from n equals 0 to infinity. So remember that cosine is alternating, starting with positive, so negative 1 to the n. And we have even powers of x over those even factorials. So we have x to the 2n over 2n factorial. So this is cosine of x. So we need to start modifying what we need here. So first, let's do this in 2 steps. What's cosine of 2x? Well, cosine of 2x is just if we substituted 2x for the x in our original series. So we still have negative 1 to the n. Now we have 2x to the 2n over 2n factorial. And then finally x cubed times cosine of 2x. So I'm going to do 2 steps in 1 here. And the reason I'm doing this is because we're going to have to take the antiderivative. I want to, instead of having 2x to the 2n, I want to separate that into its 2 and x parts. So this would just be 2 to the 2n. And we would have x to the 2n, except we're multiplying by x cubed, so that adds 3 to the power. So we're going to have x to the 2n plus 3 all over 2n factorial. Alright, so this is our Maclaurin series now for x cubed cosine of 2x. So remember, Maclaurin series means centered at 0, so that's those standard ones that you know. So this is our series. So part B says, so this was A here, part B says evaluate the indefinite integral. So now we just want to take the indefinite integral of that. So remember that you're always going to start with C plus because we have a constant of integration because we're taking an indefinite integral. And then we just need to take the antiderivative of this series. So we're still going to have our sum from n equals 0 to infinity. So everything that's not an x here is a constant. So we still have negative 1 to the n. We still have 2 to the 2n. We still, on the bottom, are going to have a 2n factorial. So the only thing that we need to do then is take the antiderivative of the x term. So remember that what we're going to do there is we're going to raise 2n plus 3 by 1 and divide by the new power as well. So we're going to get x to the 2n plus 4 over 2n plus 4. So this right there for B, that's our indefinite integral of our cosine function there. Excuse me. So what we have to do now is how many terms do we use to approximate the definite integral? So that was the indefinite integral, which is why we have a constant of integration. So now for part C, what we want to do is how many terms do you use to approximate the definite integral to 4 decimal places accuracy, and what is the upper bound of the error? Okay, so we need to do a couple of different things here. The first thing we need to do is, since we're doing a definite integral now, we don't need to have this c anymore. And in fact, we're just going to take the sum, in other words, this series here. I'm just copying this down. And we're going to evaluate this from, we have 0 to 1/2. Okay, so you can tell here from this that if we plug in 0 for n, the second part, or sorry, 0 for x, every term in that series is 0. So we don't even have to do that one. We're basically taking this sum, plugging in 1/2 for x, and then subtracting 0 because the second part of it is 0. So we don't have to do that. So really all we're doing now is plugging in 1/2 into that series. So now we're going to have everything the same, but instead of x, we're putting in 1/2 to the 2n plus 4. So this is equivalent to what I wrote on the line above. Okay, so before we actually start writing out some of the terms and seeing how we can get it to 4 decimal places of accuracy, we're going to simplify this a little bit. So remember that 1/2 to the 2n plus 4 is really like having a 2 to the 2n plus 4 on the denominator. And we have a 2 to the 2n on the numerator, so that cancels all but the 4 part of that. So most simply, we can write it with a negative 1 to the n on top. We have 2 to the 4th, 2n factorial, 2n plus 4. So like I said, that's after moving this 2 to the 2n plus 4 to the denominator and canceling out what we have. We just leave a 2 to the 4th, which is 16, on the denominator. Excuse me. So now we need to approximate this to 4 decimal places of accuracy. So what we have to do, and if you remember, this is from back when we did like the alternating series stuff, that you have to write out the first few terms and you need to find out how far you need to go so that you have a term that's smaller than the decimal, or than the accuracy you want. So 4 decimal places of accuracy is 0.0001. 1 over 10,000. So we want to keep writing out terms until we get a term that's smaller than 1 over 10,000. So let's start writing out some of the terms here. So the first term, when n equals 0, so we have 0 factorial, which is 1. We get 4 here. This is always going to be 16, and we have a positive number on top. Let me write this over here. That's our barometer. We're checking everything against 1 over 10,000. So the first term is 1 over 4, 16 times 4, because the factorial doesn't do anything when n is 0. Alright, so that's 1 over 64. That's clearly not even close to 1 over 10,000, so we got to do a couple more terms. So the next term is when n equals 1. So the top tells us this is going to be minus. Okay, so again, we're going to have the 16 every time, no matter what. Okay, when n equals 1, we get 2 factorial, which is just 2. And when n equals 1 here, we have times 2 plus 4, so we get times 6. Okay, so again, we have 1 over 16 times 12. Again, that's not a number you have to know off the top of your head. We're only trying to go as far as to see when the bottom is 10,000. 16 times 12 is obviously not 10,000, so you don't have to worry about that. Alright, next term. When n equals 2, we're back to positive. The top is always going to be 1 here. So we have 16, like always, the 2 to the 4th. Alright, when n equals 2, now we have 4 factorial. So 4 factorial is 4 times 3 times 2, that's 24. And when n equals 2 here, we get 4 plus 4, so we get 16 times 24 times 8. Alright, this is, 192 times 16. Even if you just want to estimate, if you're talking about 200 times 16, you're talking about something that's in the range of 3,000, 4,000. It's definitely not 10,000. But in terms of how fast these are increasing, you might expect the next one is going to be over 10,000, and it is, but let's just make sure. Alright, so again we have 1, we have 16 on the bottom like always. Now n equals 3, so 2 times 3 is 6. 6 factorial is going to be 720. and when n equals 3 there, we get 10. So you can see here, 720 times 10 is 7,200, and when you multiply that by 16, now you're talking about in the much higher than 10,000, 70, 80,000. Okay, so this term right here is the first one that was smaller than 1 over 10,000, which is how accurate we want it to be. So to answer the question, how many terms do you need to approximate the integral to 4 places? We only need 3. We need 1, 2, 3, because this one wouldn't have added any more accuracy because it was already smaller than what number we wanted to be within anyway. So we only need 3 terms. And what is the upper bound of the error? The upper bound of the error is this term, well, absolute value of that term, because it was negative. So whatever this is here, 7,200 times 1 over 7,200 times 16, that is the upper bound of the error. Because anything else that we go add onto this series, if you kept going with more terms, they're just going to get even smaller and smaller than that. So we need 3 terms to get this accurate within 1/10,000th to 4 decimal places. And the upper bound of the error is the absolute value of that the first term that we didn't need.